Okay, welcome back. Now we go to the OD demand estimation. I would like to talk about the background information first. Allow me to use this mode. Why the OD demand matrix estimation is important? Because we have OD demand, we have network, we have capacity, we have the traffic assignment, and by running through this demand network and the capacity into the traffic assignment package, you can provide the performance measurement. Now we have different data source, point sensor, travel time. Now we should really utilize this emerging big data sources to back calculate our OD demand matrix. Eventually, this OD demand estimation is an upper level and a low level iteration. But in my learning document, you can try to learn how the link flow proportion is being calculated. I do not have sufficient time here, so I would like to just cover some very basic material. For example, from link, we have a number of links here. You have 4 zones from zone 1, 2, 3, 4. So we have 3 links A, B, C being installed with sensors A, B, C. So you have this path flow structure as shown in this dialog, and you can try to calculate the corresponding path to link proportion or the link flow to OD flow proportion. So in this particular example, this OD pair from 1 to 3, they are going to use link A to B. OD pair 1 to 4, they are going to also use link A to B. If you have OD pair from 2 to 4, from 2 to 4, they are going to utilize link B to C because they have 2 different paths. The first path is 30%. The second path is 70%. So typically, we use this link proportion matrix to do a least square estimation to recover the OD demand matrix. Here is 2 common questions before you apply those formula in the dynamic travel assignment. Is because the travel time is not the only factor for the rule choice utility. So it's very difficult to reach this perfect travel time based user equilibrium. Second one is in the DTLI package, we try to adjust both the traffic assignment, OD demand pattern together. So, and also we know that we have this QK curve relationship. You have the free flow region, congestion region. So the link proportion is not available for density and the travel time measurement, because by drawing this particular line here, you can see for the same value of 1500 vehicles per hour per lane and the flow rate, you might have 2 different states corresponding to the same flow observation. So it's extremely difficult to calculate the link proportion in a dynamic case. So our proposed method, which published in the Transportation Research Part C paper, we have a flow-based adjustment. We also use an approximate gradient method for the further OD demand adjustment. So I'm not going to go through all the mathematical details with the demand flow, path flow, target demand flow, and the gap function. I just going through this process very roughly. We use a Lagrangian lower bound estimation to adjust all the gradient. And we have a small example in the paper and also in this slide to show you how the congested 2-link example can be adjusted. And using the simple example, we are reaching the convergence stable condition. The travel time will be convergent to the true travel time. And these are algorithmic performance and the different input conditions. And essentially, these are multi-objective programming perspective. And what we do here is a sensitivity analysis and a gradient type of adjustment. So this particular slide is quite important. We have three cases, and the free flow condition, we can have cumulative arrival count, cumulative departure count. You can have is the time axis. So, and the free flow condition, using this spatial queue, when you increase 1 unit of flow, you will have all flow being discharged after a free flow travel time. In this most important slide for the ODME, we can try to see we have cumulative arrival counts, we have the time axis. Now, if we increase just 1 unit of the flow, this increase of cumulative arrival will be always 1 unit from the entering time to the end of the congestion, so that this shaded area in this red rectangle equals to this gray area, because the height is always 1 unit. The total width is the entering time to the ending time of the congestion period. For example, I have a congestion starting from 7 to 9, entering the network or the bottleneck at 7:30. So the marginal equals to from 7:30 all the way to 9 o'clock. So the marginal delay in this area is 9 o'clock divided by 9 o'clock minus 7:30, which is 1 hour and 30 minutes. We can also do the more complicated calculation for the partial congestion link. So in this particular example, this is the time axis for the first link, for the second link, and we do literally check the propagation of the traffic flow from one link to another link. So what I want to show in this slide is you cannot just simply calculate this Q propagation using their trajectory. If you have a constant bottleneck, you need to really calculate the Q propagation from the end of the congestion period to the next link. More details, please see our transportation research policy paper. And also, Professor Michael Zhang's group has a similar discussion for the system optimal assignment by using the path marginal calculation. For the Q spillback, more complicated. So in summary, as a background information for the dynamic ODME, we have an integrated path-based demand estimation formulation. We are going to use a gradient-based path flow adjustment process. For all the details, you can try to check our source code available in the GitHub, and I hope we can provide a theoretically sound partial derivative of the link flow density and the travel time with respect to the path flow propagation. Now it's the time for us to just quickly go through this gradient-based formulation. We calculate all the gradient with respect to the path flow, and then we aggregate the changes at the origin level. So in module 6.1, in this OD estimation, we do have this one streamlined process with 3 different stages for our OD adjustment process in DTA Lite. First stage, we call this as user equilibrium. So we do use a historical OD demand pattern as a starting point. We load it, then we run the user equilibrium, for example, for 20 iterations or 40 iterations, so that we can generate this rule choice set for the second stage. In the second stage, we are reading the DTA Lite is reading the sensor data, including sensor count, sensor speed. Then we run typically 100 or 200 iterations. We try to adjust the OD demand iteration by iteration. Finally, we have estimated not just OD demand, but also estimated route path flow structure or route flow structure. By using this route flow structure, we can further do the scenario analysis. So by doing so, in the stage number 3, you can change the setup in the scenario work zone, try to see if you have a calibrated OD demand structure, how to perform the scenario analysis. To do so, step number 1, in the input link, you need to provide a mapping between the phone node and the to node and the corresponding count sensor ID. So I do have a count sensor ID here, which is exactly the same as my phone node ID and the to node ID. In other practice, you can use any other stream name as the count sensor ID and the speed sensor ID. And also in the scenario setting, in the traffic assignment method, please use number 3 as the ODME assignment method. And also we have 2 parameters for you to specify. For example, this is a 20 iteration for the first stage. Okay, the ending iteration of 50 is after stage 1 and 2. This 50 is the ending iteration number after stage 2. Okay. Now you can specify the traffic counts in this sensor count.csv file. In this CSV file, you have the count sensor ID. You can use either count sensor ID or phone node ID or to node ID to specify the location of a sensor. The Netstar and the DTA interface is available to read both type of data input. Your starting time, ending time, and the corresponding link count. When you specify the link count, be careful here, it's not lane count, it's a link count. You should be able to utilize the DTLI ODME estimation utility. Similarly, you can also provide the sensor speed.csv file to provide the corresponding speed sensor count ID and the speed information. Then you can run the simulation to perform the analysis, and you can see the corresponding user equilibrium gap at different iterations, and finally you can try to check the ODME performance by using this observed count and the simulated count in this dialog. Okay. So now it's time for me to go through the simulation in Netstar interface. In the Netstar interface, I launch the Netstar. Okay. I go to the dataset available in our package. This is the dataset number 5, ODME. Okay. Here we do utilize a dataset from Salt Lake City, or more precisely West Jordan. So you can see all those green buttons or green rectangles corresponding to the count sensor location. I can also show you here with these purple circles corresponding to the speed sensor. So under this layer sensor, you can click on and off to show the information. Under this layer, you can right click to show either the fixed count detector location or the speed sensor location. Okay. Using this menu, you should be able to generate the aggregated data and try to view the validation result as a part of output in DTLite. So I can just do that. You can specify the aggregation time interval, 60 minutes. Then those are the aggregated result by comparing the simulated travel time. Here is observed link counts and simulated travel time. You can try to utilize these observed link counts and the simulated link counts for a plot. Okay. Let's do that one more time. Simulated, observed, insert. Okay, you can try to see the corresponding information. Okay. I think we have some empty space here so that they do not show all the data sets. Going back to this menu, you can try to use other type of advanced information, such as create the reference lane and map the reference network. More information can be found in our user's guide. Okay. So let me go over step by step the Underland OD estimation facility. Let's go to the project folder. So just as I mentioned to you, go to the input link. So in this input link, we can see these two columns, count sensor ID and the speed sensor ID. Typically in the United States, the speed sensor ID is part of INRIX sensor ID or TMC sensor ID. The count sensor ID is the sensor ID provided by the state DOT. Now you can go to the sensor count or the sensor speed file. In the sensor count, you can have the count sensor ID. Okay. If you can also delete the corresponding form node ID and the tool node ID so that you solely rely on the count sensor ID to read the corresponding information. Or you can also provide only the form node ID and the tool node ID for the DTA Lite to read the corresponding sensor mapping. Link count is only input specified here. If you read the user's guide, you can also provide the link density as a part of measurement. Speed measurement, again you have this speed sensor ID and the speed for different time periods and also at a different day. Okay. Now we go to the input scenario setup. In the input scenario setting, we can specify the number of iteration. So in this case, if I want to configure this simulation setup, I should do number of iteration as, for example, I say 51. Okay. I can try to make sure, first of all, the traffic assignment mode is 3. The OD start iteration is 20. They run through this ODME to the iteration number as 50. Okay. So in this way, for the first stage, for the first 20 iteration, we run user equilibrium. For the second stage, from iteration 21 to iteration 50, we're going through this OD adjustment process. And now, after the 50 iterations, at iteration 51, we can specify the scenario work zone information to do the evaluation of different scenarios. You can have other parameters such as the maximum percentage duration with respect to the historical demand as the maximum deviation you can allow, and also the OD adjustment step. Okay. Typically, for this OD estimation mode, you should use the DTA Lite executable directly for running the DTA Lite, and then this OD estimation result including the following files. One is ODME link-based log. You can click on this ODME link-based log with information, and the ODME ROM-based log with the ROM-based information. Okay. Inside the Netstar interface, you can always use the tools, go to the sensor data management, then try to view the validation plot for link counts. So in this dialog, what you can do here is the 45-degree diagonal line. This is observed link count. Here is a simulated link counts. You can try to change different time periods. And now, by selecting this zone to link dialog, you can click and then try to find on which particular link we might not have a perfect match. Okay, this is a very convenient way for us to visualize the simulation results in this ODME process. Another trick I want to teach you here is, if you go to the link volume display, zoom in a little bit, and move all the way to the corresponding hour 16 to hour 17. Did you recognize this display? Let me just try to disable the grid background reference line. Okay. Under this volume display, you can try to increase the bandwidth. So you might see this hashed purple line. This is corresponding to the observed traffic volume. So the user can try to zoom in and zoom out, and also specify different time periods to compare how your observed traffic flow volume spatially. For example, here, this northbound direction, you got a little bit better observation and consistent in the simulation. And on this southbound direction, we don't have a good match. But be careful precisely. You need to make sure what kind of aggregation time interval you are using. If you just try to zoom in and zoom out, you may see this traffic flow volume either being simulated or being observed could have a geometrical change. So it's always a good idea for you to go to the link performance. Go to the link performance layer. Click on this layer, and then to compare this link MLE in this particular dialog. Okay, and you can always use the aggregation time interval like 1 minute, 5 minutes, or 15 minutes to compare their results. So the green line in the middle, is the current time we have in this structure. So you can try to select another link for other type of results. The display here is for the speed. For me, I'm more interested in the link volume. Okay. So by using these tools, sensor data management, you can view the validation plot for link count, for lane density, for link speed. You can try to aggregate the simulated and observed traffic measurement, and then compare the result in Excel. And we also have some additional utility to map the external line number, for example, the index TMC number, to the background DTA setup. So this ODME process is extremely complicated for the beginner, but I fully encourage you to go through this process, because this is an essential step for you to understand the big data application in transportation domain. What we need to do is, you get the network, you get the basic OD demand, you have this observed traffic count, observed traffic speed, you utilize a nonlinear optimization utility or engine inside the DTA line to do a step-by-step adjustment, and then finally you can recover the underlying OD demand structure. So all the detailed information will be provided in the learning document. We can try to show you here. Nesta document folder. Go to the Nesta package documents. This is the ODME learning documents, provided also by me and my student Zhangtao Liu at the ASU, and all the information will help you to get through this process relatively easily. Thank you.